is good administration, Singapore. No?
Yeah.
It's a
Yeah.
Chinese tradition, British tradition, and Malay tradition at the same time, no?
Yeah. Yes.
Well,
It's a very stable government.
yes. Amigos, amigas, Seminario Universidad de Desarrollo, una propuesta académica del Vicerrectorado Académico de la Universidad Nacional Mayor de San Marcos. Tenemos hoy día el honor, el placer que nos acompañe el profesor Warren Chan. Warren es decano de la Facultad de Ingeniería y tiene una experiencia en Norteamérica, en Canadá, universidades que ya han estado presentes en el seminario. Nanyang es una joven universidad, pero líder, es una de las primeras entre las 50, ¿no?, de antigüedad, es muy importante, y específicamente el profesor Warren Chan desarrolla desde su laboratorio de nanopartículas técnicas y metodologías para el tratamiento del cáncer y de enfermedades infecciosas, un área, si bien ya tiene tiempo, al mismo tiempo presenta grandes desafíos, ¿no? La aplicación de la nanotecnología en la salud humana. Well, Warren, thank you for your time, for your help. We can start, please.
Great, thank you. Let me just share my screen. Okay. Okay, let me see how I can share.
Amigos, amigas, se les comparte por el chat los links de la Universidad Nanyang Tecnológica University.
Sorry, I'm just trying to figure out how to open screen. I don't actually use Google
In the middle, you can, on square, share windows.
It says share screen, but it's blocking me. It says select a type. This site will be able to see the content.
If you like, you can send me your presentation. I can share you here.
Okay, that's great.
But email, yes.
Yeah, yeah, that would be great. Thank you. Give it 2 seconds and I will send it to you.
In my university, we have 5 faculties of engineering. The faculty of geology, industrial, chemical, system, electronics.
Okay. Oh shoot, I think my file might be too large. Let me just check. It's uploading. Give me to share screen, allow screen recording. Okay. Allow.
También se comparte por el chat el website del laboratorio que dirige Warren. De esta universidad, ya en el mes de noviembre, presentó su investigación el profesor Tan, Powering a Sustainable Future. Please, Warren, okay.
Okay, I can share now. Sorry, I had to quit out to come back in. Okay, can you share my screen? Can you see my screen?
Yes, yes,
Okay, 2 seconds. Sorry about this. Okay, I think this is okay.
yes.
Okay, great. So I'd like to start off by thanking Professor Felix for inviting me here to give this presentation. As my understanding, I think Peru and Singapore signed a recent deal to collaborate and work together, so that's wonderful. Again, as Professor Felix said, my name is Warren Chan. I'm currently a professor and a dean of engineering at Nanyang Technological University, or NTU, Singapore at this point. My home department is chemistry, chemical engineering, and biotechnology. And as he alluded to, I was at the University of Toronto for the last 22 years, and I moved to NTU Singapore in the last about a year and a half ago. So in this presentation, I have two parts. The first part is that I want to introduce NTU Singapore. And the second half, I will talk about my research that involves the development of nanoparticles for targeting solid tumors. Just want to say that NTU Singapore is located in Singapore, which is in the Southeast Asia. I had to kind of mention that because sometimes even myself, I've never really thought about moving to Singapore until they called me up and interest, and it's kind of been a good move. The university has over 30,000 students, and the students include three types of students: undergraduate students, PhD students, as well as master students. It's also one of the best universities in the world. It's ranked currently 12th in the world according to the QS ranking. And it's ranked really well. It's just because of the fact that the researchers here do progressive research that has a global impact. A lot of students are able to get excellent jobs and be placed in excellent companies, as well as that the education here is really top notch. There are 10 colleges and institutes in the university. So just to introduce a little bit about Singapore, myself, before I moved here, some of these facts I did not know too well, but now I appreciate a lot of these things. The first thing is that compared to Peru, Singapore is a really young country. It's about 60 years old. I think it's hitting 60th birthday this year. It was part of Malaysia a long time ago, and then it kind of split off about 60 years old. 60 years ago. It's a very dynamic country, lots of change, always willing to make change to advance the economy, the research, and the people of Singapore. So it's really good from that direction. It's also city state, so meaning that it's a city as well as a country all one. There are over 6 million people. It's extremely modern. Uh, the next part is that it's English speaking. So for me, who grew up in the US, I only really speak English, and it was really easy for me to adjust to in terms of the language and being able to communicate with people. There are over 40% expats in the country. So a lot of people from all different parts of the world come to Singapore and work in Singapore, and they're very welcoming of foreigners into the country. The climate is very tropical, kind of like Miami, right? And right now it's 25 degrees outside, so it's nice and warm. There's really any snow. The rain is really heavy, so it's kind of fun to watch. The next part is that it has low tax rates. So if you get a certain salary, the taxes are probably about one third that of Canada, right? So it's quite good. And it has one of the highest GDP per capita in the world, and it's one of the most livable cities in Asia. Singapore is also accessible to lots of different parts of the world. Just look at the different hours. Hong Kong is about 3, Italy is about 12, to Peru is about 26 hours. There's lots of direct flights. I think to Lima, you have to stop through Los Angeles or through Amsterdam, and then that there's direct flights from them to go to Lima, and easy to access the West Coast and East Coast of the US. The College of Engineering, of which I'm currently serving as the dean, is one of the largest colleges in NTU Singapore. There's over 10,000 students and 300 professors. It's one of the top 15 engineering colleges in the world, and it has 5 engineering schools. Or some universities call them departments, but here we call them schools. And so here's just a list of all the different schools and subjects that are covered under the College of Engineering, right? So the schools are split up into anywhere from chemistry, chemical engineering, towards mechanical engineering and aerospace engineering, which is below here. Just 2 seconds, which is here. Okay, and the College of Engineering actually faculty demographic is very broad. As I mentioned, NTU Singapore welcomes everybody into the university, both at the undergraduate, the graduate, as well as the faculty level. Most of the faculty are trained in North America or in Europe or in Asia nowadays, and researchers are from all nationalities, Asian and non-Asian as well. And some faculty become Singaporean permanent residents and citizens, and others decide to maintain their own citizenship, right? So there's a lot of flexibility in terms of what you want to do if you are here. So, in a nutshell, this is Singapore. I'm still learning a lot about Singapore. As I mentioned, I moved here about 18 months ago, and so it's been a really nice place to live. Very order, very structured, and there's lots of things to do. And it's also been quite fun for me to be able to travel to different parts of Asia, places I've never been to myself, like in Bali in Indonesia or Bangkok in Thailand, right? And there's a few more trips I plan to make the next year or two. So it's been a lot of fun from a professional and a personal perspective. Okay, so I think we're gonna switch gears and talk more about science and what my research lab does in Toronto and now at NTU Singapore. What we work on is a topic called delivery and delivery technologies. And delivery just refers to the ability to bring a substance from outside the body into a specific target cells and tissues. And it's a really important topic because many drugs has to get to a specific tissue or cell for them to work properly. So what I have here listed on the left is all the different kind of therapeutics that has been developed for the last 20 years. Genome editors, immunotherapy, engineered proteins are some examples. A lot of companies in the world started based on the development of these therapeutics, but many of these therapeutics have failed in clinical trials. So when they fail in clinical trial, they would never be used in humans. And the main reason they failed in clinical trials is because these therapeutics cannot be delivered to the target sites. For example, they can't be delivered into tumors, which then affects its ability to treat cancer. It can't be delivered into pancreas, which affects its ability to treat diabetes. So again, you have to bring enough of the therapeutics to a target site for it to be effective. And a principle that has been very common the last bunch of years is to take these therapeutics and place it in a nanoparticle. A nanoparticle essentially is a structure that is typically below 100 nanometers. And what you do is you take the drug and you place it inside of a nanoparticle. Then you inject the nanoparticle into a patient. They circulate around, and you can program the nanoparticle to release drugs at the targeted sites. In this example, if you release the drugs, it essentially kills the tumor cells. And the impact of this is putting the drug in nanoparticles is that it would increase the therapeutic effectiveness and decrease the side effects that a patient experiences with the therapeutics. And from an engineering perspective, the way we've been designing these nanoparticles is based on a principle called the enhanced permeability and retention effect. In this principle, it suggests that when the nanoparticle is injected into the bloodstream, it travels around, it's delivered into the tumor because the nanoparticles, as it circulates through the vessel, transports through gaps between the endothelial cells, which is shown here. The nanoparticle goes into the tumor, and what happens, it accumulates and retains in a tumor because they do not exit from the tumor. And the reason they do not exit from the tumor is because the lymphatic system is broken. And because it's broken, you have nanoparticles pool in the tumor. And because of this concept, the engineers have been designing nanoparticles based on two main principles. One is circulation half-life, meaning the nanoparticle stays in the bloodstream for as long as possible. So you design the chemistry and the particle size to allow it to stay as long as possible in the bloodstream. And then if it stays along in the bloodstream, there's a higher probability of it getting inside the tumor if the particle is small enough to go through the gaps. So two engineering principles. increase circulation lifetime and decrease the nanoparticle size so that it is smaller than the gap to get into the tumor. Using this particular mechanism to guide the design of nanoparticles has been a problem because after 30 to plus years, there's less than 15 nanoparticles that's been translated into patient care, meaning that it's these particles with the therapeutics is very few of them are being used in human patients at this particular point. However, publication-wise, there are thousands of papers per year, right? So there's a disconnect between translation and academic publication. And so what we started looking at about 10 years ago is what is the cause of this particular problem? And we start to measure what's called delivery efficiency. So what happens is that you inject 100 nanoparticles into a patient. We ask the question, how many of those nanoparticles will enter into the tumor? And we found that less than 0.7% of the nanoparticles will be delivered into the tumor. And the reason for that is because when the nanoparticles are injected in and in circulation, there's a lot of other organs that compete for the nanoparticles, such as the liver, spleen, bone marrow, and so on. And most of the time, they outcompete the tumor for the nanoparticle. And if you try to deliver it to a tumor cells, once it gets into the tumor microenvironment, you also have very little nanoparticles get into the tumor cells. And the reason for that is because as it goes through the tumor, you have other cells that will compete for the nanoparticle, and you have things like the extracellular matrix that blocks the transport nanoparticle. And if it gets into the cells, they have to escape certain organelles to get into other organelles that you're trying to target. And so it has to escape things like the lysosomes, endosomes, and so on. So really, if you inject 1 million nanoparticle into the body, 7,000 of those will get into the tumor, 14 into tumor cells, and only 1 into the nucleus. So what ends up happening is that this analysis shows us that there's a delivery efficiency problem. So not enough of the nanoparticles you inject in will get to the tumor for it to elicit its effect. And this is one of the cause for the low clinical translation of nanoparticles. So what my lab has been trying to do the last 10 years has been trying to solve this delivery problem. How do we increase the amount of nanoparticles delivered to a tumor from 0.7% towards 5 to 10%, a value that we calculated to lead to therapeutic effectiveness in humans? And so what my lab has been doing has been mapping the journey of the nanoparticle. So once the nanoparticle is injected into the bloodstream, what happens to nanoparticles in the blood? What happens to nanoparticles in the liver? What happens to nanoparticles in the spleen? What happens to nanoparticles in the tumor? So again, you map the journey of the nanoparticle, it will be able to tell you what the problem is and how to actually solve the problem. And so here, I'm just going to focus my talk on 3 specific sites. So we assume that the nanoparticles can circulate for a long period of time. If they circulate for a long period of time, they have to be able to enter the tumor for them to be delivered. They have to be retained in the tumor, and then they have to probably eventually leave the tumor. So we tested these ideas. And again, these are the 3 steps of the EPR principle. And so we broke these 3 steps up into 3 detailed studies and published 3 separate papers on these particular aspects of the transport into the tumor. And then what we hope is that once we put the 3 studies separately, then we can put it together and have a full picture as to what's going on with the nanoparticles delivered to the tumor. And the first thing I would just want to show you is an intravital image of a nanoparticle traveling through the tumor. So just to give a brief overview of what we're doing, we take a nanoparticle, we inject it into a mouse that has a tumor. We place the tumor under an intravital microscope, and we can image the nanoparticles moving through the bloodstream. So in this S-shaped structure, that is a tumor blood vessel. The little speckles that you will see are the gold nanoparticles that we label with different fluorescent agent. Okay. So you can see that the nanoparticles are moving in the blood vessel, and then you can see at certain points, the nanoparticles leave the vessel and then enter into the tumor microenvironment, which is essentially the black region. So most of the cells that we're trying to target are in the black region. So once it leaves this vessel, it essentially goes to this space, and then eventually it will move around and find its cell. But what we found is that the nanoparticles do not actually go through gaps between the endothelial cells as stated by the enhanced permeability and retention effect. But what we observe is that the nanoparticles enter into the tumor through the endothelial cells, which is shown here. So they enter through these packets, these vesicles, right? Where you see lots of nanoparticles, and then essentially goes from outside through the cells into the tumor microenvironment. And we name these cells nanoparticle transport endothelial cells. So within a tumor system, within the vessel, usually about 20% of the endothelial cells are able to transport nanoparticles from the blood vessel into the tumor microenvironment, right? And we're still trying to figure out what's so special about these cells that govern the transport process. We also then later on, a couple of years later after that study, we found the mechanism by which it transports through. And the way this works is that as the nanoparticles flow through the bloodstream, the cells produce little arms called ruffles. And what happens is nanoparticle goes through these ruffles, then captures the nanoparticles and essentially captures the nanoparticles. And eventually this ruffle closes down, which is here. And then the nanoparticles are trapped in a vesicle. And then eventually goes to the other side and then dumps the nanoparticles out into the tumor microenvironment. And you can actually see the nanoparticles here leaving the endothelial cells into the microenvironment. The actual diameter and size of these closed ruffles are about 200 to 300 nanometers. So anything that's below this particular size can be transported into the cells and exit out through the other side of the cell. And what we found is that aside from these ruffle process to drive transport, there are also other mechanisms that can also drive transport. And one of them is actually a receptor base, meaning that the cells produce certain receptors, and thus receptors binds onto ligands on the surface of nanoparticles and drives them into the cells. We don't know if these particular nanoparticles release out on the other end, but we do know they essentially get taken up by this process. The way we know this is we actually took the endothelial cells that contain nanoparticles and we did RNA sequencing analysis. And we also found genes that are related to a clathrin or caveolin process, which is typically associated with these receptor capture of nanoparticles with ligands. And then we mapped out the size versus the pathway they take to transport into the endothelial cells and out. And we found that the dominant mechanism is the non-receptor ruffle-based scheme. And the receptor base does participate, but participate at a much lower level to transport into the tumor. And so now once the nanoparticle exits out of the endothelial cells and gets into the microenvironment, the question is how do they penetrate or move through the tumor microenvironment? And one process is that if the nanoparticle is very slow, they just naturally diffuse out of the bloodstream into the microenvironment and slowly moves through the tumor interstitial space, right? And the tumor interstitial space basically contains a lot of collagen gel. It contains a lot of collagen protein. So the collagen proteins is viscous and thick. So the particles, they're small enough they actually get through different pores within that thick layer. But if they are larger, let's say they're about 20 nanometers and higher, they have more difficulties in terms of transporting through the extracellular matrix. So then we found in 2022 a different mechanism of how nanoparticles transport. So once they get through the endothelial cells, they get through the tumor microenvironment, and then somehow the tumor-associated macrophages starts to move toward these nanoparticles. And then the nanoparticles essentially gets taken up by these cells, and these cells then carry the nanoparticles out from the initial site of entry for the nanoparticle. So these cells are also transporting nanoparticles from the site of transport into different regions of the cell. And again, I have an intravital image here, which shows this process. You can see the white, which is the nickel nanoparticles that are in place. And then these cells are called tumor-associated macrophages. And you can see it labeled in blue, and you can see this guy moving around. So it moves around until it finds nanoparticles. Once it finds nanoparticles, it starts to eat up the nanoparticles. And then once they eat up the nanoparticles, then the cell starts to move to different regions outside of that particular space, right? We still don't know what happens to the fate of these cells once they leave this particular initial spot of eating of the nanoparticles. But those are studies that are being are occurring at this point in my research lab at NTU. So, and the last experiment to show you is that nanoparticles do exit from the tumor, and this experiment is pretty straightforward. What we did is we take nanoparticles, inject it in the tumor, and we actually image the lymphatic vessels. And what you see here is that the lymphatic vessels get all lit up from the nanoparticles, and so it exits out of the tumor through the lymphatic system, and then reconnects with the heart for the next circulation. So it goes from the lymphatics back into the blood vessel, and then it has another chance to enter into the tumor. So what this shows is that the nanoparticle lymphatic system, the lymphatic system is not broken. It does not trap nanoparticles in the tumor, but it actually allows exits. Basically, nanoparticle can exit out through the lymph system. Okay, so because of these three studies, we now reframe the mechanisms of driving nanoparticle transport. And we call this mechanism the active transport or retention principle. And what we propose is that as the nanoparticles gets injected into the patient, they circulate around. The nanoparticles predominantly go through endothelial cells and not through gaps between the endothelial cells. It gets transported into the tumor microenvironment. And in a tumor microenvironment, it slows down because they're interacting with different cellular component as well as a cell component in the tumor. And then eventually they exit out of the tumor through the lymphatic system. It will transport through the lymphatic system and then eventually comes back to the bloodstream to be able to recirculate again. And the overall now mechanism of how nanoparticles are transported in the body is the following. So when you take a nanoparticle, you inject it into the patient, the nanoparticle absorbs serum proteins onto the surface. As it moves through the bloodstream, it starts to interact with different cells. In this example here, it interacts with Kupffer cells, which are lining the liver. And as it goes through the liver sinusoids, the Kupffer cells has potential to take up the nanoparticles. If it takes up nanoparticles, it removes them from circulation. And if it escapes these Kupffer cells, it goes back in circulation. Then what it does is it goes through the endothelial cells, slows down in the tumor microenvironment, then and then leaves through the lymphatic system, transports to the lymphatic systems, and then goes back in circulation. Essentially, all these organs are competing for the nanoparticle. So delivery is low in the tumors because it's losing its competition for the nanoparticles with other organs and tissue. And this competition is driven by the way the ligands here interact with the receptors or non-receptor based structures of different organs and tissues. And before I left Toronto, I developed the video of this entire process, so from 20 years of work, to explain how nanoparticle delivery works. And I'll show it here. Yeah, so the what we've done now is revise this 40-year-old mechanism that governed the design of nanoparticles. And this now is going from the EPR principle, the enhanced permeability and retention principle, to the active transport retention principle. And what the reason this is important because it starts to change our approach to designing delivery systems. So rather than focus on size and circulation, you have to focus on redesigning either the nanoparticle for transport through cells, or you have to redesign the biology so that it wants nanoparticles to be transported through. So this now opens a completely new area of research in terms of designing nanoparticle delivery systems. And what you can do now is to be able to redesign it so that the therapeutics I mentioned at the beginning now become more effectively delivered to the target site. So really the next step for us in the next 5 to 10 years is really to understand the molecular cause that influence the transport nanoparticles in the bloodstream. And then once you do this, then we can move to our application because those specific molecular understanding gives us very specific targets by which we can change to be able to enhance or decrease the delivery of nanoparticles to a specific tumor site. Again, right now, one of the biggest topics is really delivery, right? Because this is the bottleneck to translate all these drugs for treating these variety of diseases. And these diseases encompass about 70% of the diseases that humans face. So if we solve the delivery problem, even if we address 10% of the 70%, it's going to lead to saving the lives of millions of people very quickly and very rapidly. So, but delivery again is very complicated because the human body is designed to try to reject everything you introduce into the system that it doesn't want. And so that's what we have to solve at this particular point moving forward. So with that being said, this is my research group. They visited me in Singapore last year for a conference. So they are really excellent and really pushing the boundary of science. These are the students that actually develop a lot of these ideas that I mentioned in this particular project, from the researchers that develop the understanding how nanoparticles enter tumor, to the discovery of the NTEX, which has been here, to understand the molecular mechanisms that govern the transport process, as well as a long list of collaborators. I've been very fortunate through the last 20 plus years with a lot of really good people working with me in different areas and different angles that have really shaped this research theme and project, as well as the funding support. Canada was very supportive of this fundamental type research that led to us redefining the mechanism of nanoparticle tumor transport that can potentially enhance both the economy of companies or countries, as well as can save lives of patients, if we can actually translate these ideas now into real products to help patients. With that, thank you for inviting me again, and I'm happy to address any questions you may have on this particular topic.
Thank you, Warren. Warren, in this moment, we can see about some years ago, the global challenge, the pandemic, no? COVID-19, no? So the people wait the next pandemic, no? Only some years, but
Yes.
it's probably we can see in 10 years a pandemic similar to COVID-19, no? Because the tropical is very difficult for the urbanization, the climate change, etc. No, so this is we live in this moment and transitional age. No, this is in the politics, technology, energy, etc. No? So in this context, how is you connect your proposal, your study, your research about the nanoparticles and the health, human health, in this context, no, the imminent, no, pandemic in 10 years or 20 years?
Yeah, so the pandemic, there's always new infectious pathogens that are arising, and that's going to affect the world, right? And what the nanoparticles do is that it creates a storage system to deliver the drugs to the target. So we saw with COVID-19, the vaccine is developed by putting mRNA inside a lipid nanoparticle. The lipid nanoparticle was initially developed for cancer and other applications, but when the mRNA is developed, everyone realizes that the mRNA cannot just be injected into the bloodstream because the body has enzymes to degrade them. So you put inside nanoparticles, it protects the mRNA from degradation and allows it to be delivered into certain cells. With COVID-19, the target cells were very close to the muscle, so it's close to a certain structure. So delivery tends to be very focused. But if the infectious pathogen infects the patient's cell that's in different regions in the body, then you actually need a different nanoparticle design to be able to carry that therapeutics to that particular target site, right? So in order to be able to design these particles for that particular application, you have to understand how the nanoparticles work. Now imagine if lipid nanoparticles were never really developed. If it was not developed, we would still be in a pandemic state with COVID-19, right? Because we did not have a therapeutic agent to be able to attack the infectious pathogen, right? So sometimes in research development, you develop for one application, but when there's a new medical problem rises, that technology can be applied to that particular new medical problem. And that is why it's really important to do fundamental basic studies, because it teaches you how things work. And once you know how things work, we can engineer it in a different ways to address different problems.
Well, in 10 years, in 5 years, we can see the development, the intelligent artificial, no? The artificial intelligence. Yeah. So the artificial intelligence help research and modeling different, no?
Yes.
Context, different situation. This artificial intelligence with the big data center, no? We can see in different country the strong computer. So in your research, how do you project this data center, artificial intelligence in the health you research with nanoparticles and the human health?
Yeah. So artificial intelligence will be very important in terms of hoping to design the best nanoparticle design for targeting applications. When we essentially have to increase delivery, it still relates to the nanoparticle size, shape, and surface chemistry, as well as other properties. So when you look at the combination of properties, it could reach hundreds of thousands to millions. And so you need to use artificial intelligence to teach you essentially which design is best for targeting which disease tissue and pathology. The challenge of using artificial intelligence for this particular applications at this point is that there's not enough data fed into the machine learning algorithm for it to learn what is the best size, shape, surface chemistry. And so that is still at a development stage at this particular point. I just want to mention that this area of research is called nanobio interaction. So we started this field around 2013, and it's only been around for 12 years. But since 2013, there's been a lot of development from lots of researchers from the world in terms of understanding how design relates to delivery. And we're just starting to put this information into machine learning algorithms, which then allows us to develop predictive model, which then allows us to use artificial intelligence to identify the best design for the specific application.
Warren, in physics, in 20th century, you start with the mechanical approach, and the last, you finish with the post-mechanical approach, no? The Newtonian physics and the post-Newton physics with the Heisenberg principle, so the subjective in the reality, in the context. So you can project this aspect, because human is very complex, It's very complex, the human, the cells, with a traditional approach, classical approach, is very difficult to track the cell. So you can project, imagine no orthodox, an orthodox approach to this problem for the nanoparticles to tracking the tumor cell and the tumor. I don't know, with the traditional approach is the Western approach, no? But in the physics, in the middle 20th century, some physics recognize some part the Buddhists connect with the quantum physics, for example. So it's very, very difficult, no? Because the people seeing the physics is very objective, the physics is mathematical, so it's how connect no orthodoxal or oriental approach to the physics. But some physics in last 20th century recognize this connection, no, between integration the subjective and the objective goals approach. So, uh, how do you experience with this no orthodoxal connection of nanoparticles in human health?
Yeah, so I can tell you that the 20th century physics actually dominated because a lot of physical principles were used to explain processes. What happened around probably around the late 1990s is that with the sequencing of the human genome, is that we moved into a molecular stage, right? So in the 21st century and beyond for human health, it's really about molecules because at the end, as a human, we're defined by tissues, cells, and if you go down to the basic levels, it's actually molecules. And we're essentially now defining what those molecules are that defines the disease and that defines who we are. So that's one part. This is probably going to take another maybe 20 to 40 years to figure out some of these aspects of who we are as a human being. Then what you're going to see is that the physics will combine with the molecular part to create a better understanding of physical process as it relates to how biology works. And then you can actually develop computational schemes that allows you to predict how changes in molecules affects human health and how changes in things like nanoparticles relate to the physics of transport and then how do they relate to the molecular biology of a human. And so combined, we are actually now going to merge in different centuries, different principles to create new principles that creates a more accurate way of treating disease, right? And we're going to be treating disease at the molecular level rather than at the cell tissue or the symptom level. And it creates greater precision in disease treatment. This part of the equation is really important because every human individual may be different molecularly because they may be different molecularly. How we respond to drugs, how we respond to things like nanoparticles may be different, right? And so we're going to be able to precisely be able to identify what causes disease and then be able to precisely determine what's the best strategy to transport drugs to the target site, as well as what precisely, which drug precisely can treat that particular disease, right? That's why the therapeutics I mentioned, there's so much excitement toward it because those are very precision drugs. It's just at this point, we don't know how to deliver them to the target site.
Yes, for example, in education, in the Renaissance time, the arts and science are the same objective for the Michelangelo, Leonardo da Vinci. In 19th century, separate arts and science.
Yep.
The human in education, in the beginnings, the people believe in common education, but in the middle 20th century, decide no, it's education for different people, no, different
Yes.
people, different students need a special education. So yes, a disease is a unique experience. Yes,
Yep.
we have common aspect, but each people is different. In this, similar to the equation, no? One student need a personal, a specific approach. Yes, you can see in general education, but for the top people need a personal, no? A personal
Yep.
education. In the health is a personal experience. One person is a cosmos, is a universe, it's very complex. So we can the people told about the genetics about the race, no, the genetic connect the language, connect the history, so we can connect the people and the disease in the past, no, the Africans, the Europeans, the Indian, the Chinese, the Indian, American Indian. So this aspect, the different race, the different ethnic people, do you consider in your research? Because this for the Western communities, is for the Oriental communities. We can find this difference in the treatment, the human health.
Yeah, so in these research at this point, we have not considered ethnicity because the mouse models we use aren't defined by that particular scheme, right? What we did do a few years ago in a study is that we looked at serum protein absorption onto the surface of nanoparticles from human patients that are from different ethnic background as well as different age. And we found that the proteins that absorb to the surface are different, right? And so because they're different, they likely, based on our individual biology, it would affect the targeting of the nanoparticles at different sites, right? So as we start to move to the next stage, once we finish up our studies with mouse models, and you start to see how the concepts apply to humans in things like clinical trials, as well as in use, then you can start to map that part of the equation out and understand how different ethnic groups and age influence how particles are delivered from outside the body into the specific sites. But that would probably be 10 to 20 years from now, but it would be exciting to see.
In this moment, the people say, well, in some years, about the connection between the biota in the intestine, biota, connection with the nutrition. So inside ours, we have a microbacterial we we develop with own food, own nutrition. So this is special relationship between our body and our macrobacterial inside intestine, for example. So this uh, relationship how connect with your research because it's common for human living with the other uh, bacterium inside in the beginning, the human race until now. So the human life is a experience with different body inside ours, no bacterial.
Yeah,
Yeah, this
yeah,
is
yeah.
bacterial is different, but it's a successful relationship in the thousand years ago, no? And this special relationship could be uh, contact with your research, the nanoparticles to tracking the tumors and no, the disease.
Yeah, so a lot of so you are correct. The microbiome tends to vary quite a bit in terms of people. There are a lot of researchers that are working on developing nanoparticles to target specific microbiome to change the population. Unfortunately, I actually don't work in that area at this particular point, but it is really important to target and change the bacterial population in the body because it may have also an impact on blood proteins, immune response, and other types of medical properties that we all face.
Well, amigos, amigas, ¿tienen algún comentario, alguna pregunta, por favor? Warren, St. Mark has a tropical institute Tropical Disease Institute, more 50 years old. So the tropical disease could be a common topic between Singapore and Peru, Lima and Singapore, no? The other is the rainforest, the destruction of the rainforest is a challenge for the urban population. Indonesia, Malaysia, no, is near to Singapore, so there are challenge for Singapore, no, in neighbor the Indonesia, because in the forest is home the different disease, and this disease with the climate change could no came to the city, no. So
Yes.
it's similar. Amazonia, Peru, and Brazil is a big natural, but at the same time is a chain because of the human activity. So the bacteria, virus, the tropical rainforest is more connect with the cities, the village, and the common population. So I believe this topic, the tropical disease and the rainforest as a challenge for the urban population could be both topic developed for Singapore and Lima and Singapore.
The answer is yes, you are correct. Infectious disease environment is a big research topic here in Singapore, right? And I think they have invested a lot of money in creating mostly pandemic preparedness, infectious disease research. And my lab here is actually right next to the level 3 facility, right? To be able to allow them to study different kind of infectious pathogens. And from a climate perspective, there's a lot of interest in climate change. There's interest in environmental impact and sustainability. And the reason is because, Singapore is a small island. It's surrounded by water. And it's the way it's structured is that these potential natural issues or disasters can affect the city quite significantly, right? And as you know, like near here, there's a lot of also on rainforest, forest, infectious disease can pop out anywhere. Infectious pathogens can pop out anywhere. So there's a lot of focus on environmental issues as it relates to diseases.
Uh, Warren, yes, Lima is distant from to Singapore and Lima, but in the year could be the opportunity to visit your university, especially your laboratory, no? What mode in the year do you recommend for a professor from San Mark could be possible to visit Nanyang and visit your laboratory in the year?
Yeah, I think it's possible. It just depends on how it's done, right? On an individual basis, that's usually with the professor. The other approach to do this is actually at the university level. We have an international partnerships office, right? So they actually help coordinate visits between universities. And then you can see the university as a whole, and then there's specific areas or labs that are of interest, and they can also work with that context, right? And the international partnership office is quite good in the sense that, if there are official partnerships that's, let's say, being built between your university and NTU, it would have to go through that office as well as, that office to start the process, right? We've built a lot of partnerships since I even been here, and it's usually coordinated by that office. Some of the partnerships are actually for faculty exchange. So some faculties that might go to your university, some faculties at your university might come here. The other one that's actually useful is a student exchange, right? So from undergraduate level to the graduate level, especially at the graduate level, I think one thing I didn't mention, right, is at the graduate level, there's a lot of fellowships that pays for a graduate student to be educated in NTU Singapore, and so these fellowships allow training, and then it's actually quite good in the sense that a lot of the students that get trained here until they return back to the country and they bring some of the concepts and ideas through. And I think it may also work the other way as well, right? So this is a way to do exchange. And so again, as a university to university, the partnerships usually involve, but if it's professor to professor, then it doesn't need to involve the university. Then those can be discussed at the faculty level, and then, but we still have to inform the university. So that's the process.
Well, this over summer, in different the north, in the south, in the January, February summer, over summer. In this next summer, professor from Milano University, from Sao Paulo University, no, it's possible to deliver or give us course, virtual course, to two class, three session, two session, one session per week. So in the next summer, could be possible invite your laboratory to give an introduction to this topic or research for the top student. No, could be 2 or 3 session, virtual session. This time is the best for us, and I think for you for in Singapore in the morning. In the past, I developed a program with the Fudan University, San Marcos University, early Saturday, night Friday, connect the student, the top student, the Fudan to the San Mark about the society and culture in Trans-Pacific region. One semester, no, in the year 23, 20 students Fudan, 20 students the San Mark. So cool, it was a beautiful experience. So this proposal, no, this experience could be for Nayam possible. Connect the students, the top student, one session per week. In the holiday, could be July, could be February, to share, no, to share experience about the research and the on research. I think for the student could be very special experience.
Yes, so that is a possibility. Why don't we talk offline after this presentation? If you just send me an email of what you're thinking of, then I can look at it and see what's possible.
Yes, we have time. We have time for projects, common activities. The first activity with Professor Tan, the electrical electronic department from your college, the engineering. The second, your presentation as Dean, the College of Engineering. Thank you very much for your help and time. In San Mark, we have some department de biomedical engineering. No, it's 6 years start ago, and now we inaugurate a department de nuclear engineering. So in San Mark, we have 16 department engineering. So I believe, I think we can opportunity to different aspects of engineering to thinking how to connect the student and the professor. Well, amigos, amigas, ¿tienen alguna pregunta, algún comentario? Well, Warren, I hope that you can visit Lima. We have time, 26, 27, to know our research in the engineering and the health. Yes. The faculty, the human health, is a top faculty in our country, the San Mark faculty, the medicine, in coast of South America is Chile, Peru, Ecuador, and Colombia, 4 countries, and the principal university in Chile, Santiago, University of Chile, Peru, University of San Mark. So Singapore has agreement with some Chilean university. Is probably project this Chilean and Singapore experience to the Peru to connect with this region. There are in projection in the Pacific market, Pacific community, the China, ASEAN to South America. So I think the future is part the South. No, this moment will live a different dialogue between the North and the South. In this new dialogue, Singapore, Peru, Brazil, no, is leaders, no, leaders in the 21st century.
Yes, the world is changing, right? There's a lot of interesting new developments, and the South is playing an important part in the overall system and cycle nowadays, right? So, yeah, no, I look forward to visiting. It would be great to visit. So I'll look at it in 2026, 2027. I can't believe we're in 2026, 2027 already. So thank you for the invitation for the talk. And I look forward to continue our discussion as we start to build partnerships together moving forward.
Peru has a big Chinese community in the 19th century from Cantonese immigration in middle 19th century. So in this moment, the 10% the Peruvian population has Chinese origins, for example. It's a special country in the South America, different to the Brazil, Argentina, Colombia, and Chile. Your surname is Chang.
Yeah. Yeah, no, that's amazing.
I believe your family from China.
Yeah, I was originally, I mean, it's from the region that I'm from, or my ancestors are from, right? In China, the ones that left China a long time ago, right? They're from southern China in the Canton regions, right? And so they're the most adventurous Chinese. And so when they went to Peru 2 years ago, I was in Central America. So there's a lot of people, Chinese people from several generations now that are from that region of China. Same thing in the US in the 1980s. 90% of the US was from that region of China, right? That immigrated in the 1819, early 2000 era, early 20th century, right? Into the Americas. So.
Yes, the Chinese diaspora is in all the world.
Yeah.
Well, I would like to express appreciation from the authorities to your university, to the leadership, especially for you, Warren, and I hope continue this activity.
Thank you very much. I look forward to chatting more in the future.
Amigos, amigas, muchas gracias por su presencia. ¿Podrían prender sus cámaras para tomar una captura de la sesión? Please, you can open your camera for a picture, please. Wait a moment. Mañana nos acompaña la Facultad de Medicina de Sao Paulo, que comparte su curso de verano de julio del año 26. Un momento. Ok. Víctor, un gran saludo. Gracias.
Gracias.
A ver, un momento. Vamos a hacer la captura. 1, 2. 1, 2. Ok. Well, thank you. Muchas gracias, amigos y amigas. Mañana a las 2 de la tarde, la Facultad de Medicina de la Universidad de Sao Paulo nos presenta su curso de verano, julio del 26. Warren, I hope we can continue. Thank you.
Yeah, thank you very much. Have a good day or night. I lose track. I just started my day. So
Yes.
thank you.
Pues,
Thank you.
bye. Thank you.
Bye-bye.
Gracias.